Hi everyone, this is Ranjit and welcome to the next video in our GeomAlgoLib series. We are currently in the process of writing our own ConvexHull algorithm, and I already made 2 videos covering this topic of convex hulls in 3D. If you haven't seen those videos, I'd strongly recommend that you go and check them out. You should be able to find the links in the description. In the last video, we wrote down all the logic that's necessary for our convex hull algorithm, but in this logic, we use a lot of functions for which we haven't written any definitions yet. They're just declarations at this point. So to actually get this code running, we have to add these definitions, and that's what we will be doing in this video. So all these functions don't have definitions yet, so we have to add these definitions. So let's try and do that. Let's add a definition for the setFace function. Okay, so the first thing we want to do inside the setFace function is to assign the face a proper normal, because the constructor of the face doesn't assign a normal because the face itself doesn't have any information that it can use to calculate this normal. The face just has the indices of the vertices, but you need the actual positions of the vertices to calculate the normal, and the positions are inside the hull. So let's just we called it face. So let's just assign face.normal equals, so we're going to have to get the vectors that represent the edges and then do a cross product of these vectors and then take a unit vector, because our normal has to be a unit vector, because it's only about the direction. We don't care about the magnitude. Magnitude doesn't mean anything for us. Okay. Let's take the vertex corresponding to the B index and subtract it from the A. So that gives us the vector from A to B. And then we take a dot product of that, cross product of that with the other edge vector. And then for the whole thing, we're going to calculate the unit vector. So that gives us the normal of the face, but we don't know how this face was oriented when we get it inside this function. It could have been oriented correctly or it could have been oriented incorrectly. So we're not completely sure whether this is the normal or this is the opposite of the normal. And the way we do that is to check if this face is visible from our center. So face visible, face, and center. It's called M center. So if it's visible from the center, then something's wrong, like the face is oriented incorrectly. So we need to flip this face. So earlier I said that the M center represents the center of mass of all the vertices, like the average of all the vertices. I was incorrect. In fact, I would have to go into the constructor and just remove the line where we assign to this field. This center has to be the average of the 4 vertices that we use to construct the initial simplex. So, because that is the actual point that we can be sure is inside the convex hull all the time. Because we create the initial simplex and the center of the average of the 4 vertices of the simplex is definitely inside the simplex, and from that point on we only grow the convex hull, so the center should remain inside the convex hull the whole time. So if our new face is facing, like if it's visible from the center, we flip it. And then we insert, now that we've oriented the face, we insert it into our map. So we use the insert or assign. The key will be the face's ID and the value will be the face itself. And then we have to loop over the edges of the face and add it to our edge face map so that we know that this face is connected to the 3 edges that it has. So because the number of edges is just 3, I'm going to use char data type instead of size t, and the number of iterations for this loop is going to be 3. Okay, so we're going to have to add this face to our edge face map member, and the key for this map is the edge itself. And we already have a method to get a certain edge of a face. So let's just use that, face.edge, and pass the index of the edge. So that's the key. And to that index pair, the value is also another index pair. We want to add the ID of the face itself. So add face.id. So this method, add method, if you peek into the definition, returns a Boolean. So what this method does is checks to see if either P or Q is vacant. By vacant, I mean whether it has a -1 in it, which is just a vacant spot for an actual valid index, right? If either P or Q have this invalid index in them, it just assigns that field to the given index and returns true because it successfully added the index. But if P and Q already have valid indices, then it will not add the given index and it will return false, which means it failed to add the given index. So let's just honor that Boolean by checking if the addition of the index was successful or not. And if it wasn't successful, let's throw an exception. Failed to add face to the edge map. So that is everything we need to do to add this face to our convex hull. Let's switch back to the header file one more time. Okay, now let's write the logic for the pop face function. So first, let's create a local variable to store the face that we're going to pop. And we received the index of the face that we need to pop. Well, it's actually the ID, so let's just rename this parameter, because index implies some sort of continuous index, but the purpose of this is just to keep the faces unique, so it's an ID. So we don't even know whether this face has already been popped or not. So we need to check if this face exists. So if get face, ID and face. So this getFace method only returns true if a face with this given ID was actually in the convex hull at this point in time. If it's not, then we just return this invalid face, because the default constructor for the face creates an invalid face, so we just return that. But if we do find a face in the convex hull with a given ID, we need to actually do some more things. So we need to first remove the face from our face map, and faces arrays ID. And we need to process the edges of this face and the adjacent faces connected to this face over these edges. So to do that, let's create some local variables for storing the edges and the pair of faces connected to each of the edges. And let's create a local variable to store the adjacent face ID. Now let's loop over all the edges. Because there's only 3 edges, we're going to use the char type. And EI stands for edge index. And let's get the edge of the face that we just removed from the convex hull. So we're looping over each edge, and we retrieved that edge from the face. And we need to set this edge to the output parameter edges. Okay, so for each of these edges, we need to get the faces that are connected to these edges using our getEdgeFaces method. We pass the edge and the index pair that we want to populate with the face IDs. And if this method actually finds some faces, then it returns a true. If it doesn't, then it returns a false. So if we don't find any face on this edge, then we can continue. But we need to do one more thing. So we need to set the adjacent face corresponding to this edge as an invalid face. which we have as an unset instance of the face, and then we continue. But if we do find a face, we need to check that the pair of faces that we found contains the face that we just popped, because if it doesn't, then something is seriously wrong with the algorithm, because we popped a face and its own edge didn't know that it used to be connected to the face that we just popped. So let's just check if pair dot contains the ID of the face. So if it doesn't contain the ID, then once again we bail out. In fact, we don't have to do face.id, we can just do ID because we already have that in the parameter. So now that we found a valid pair of faces, and we know that the face that we just popped belonged to this pair, we can remove it by calling the unset method of the face pair. So we removed the ID of the popped face from the pair of indices. So let's just set this back to our map. Now we need to get the index of the adjacent face. So because we've removed the index of the popped face from the index pair, the only remaining valid index is that of the adjacent face. So we can just do if p equals -1, if p is an invalid index, take the q. If not, then take the p. Because we know for sure that only one of these indices has to be valid, because we just removed the other one. Now we have the index of the adjacent face, but let's try to get the face itself. So we want to store this face in this output parameter, adjacent faces at the index EI. And if we didn't find a valid face, let's just set this to an unset face. So to recap, we looked for a face with the given index. When we found it, we removed it, and then we looped through all the edges of this face that we just removed. And for each edge, we tried to get the other face that's connected to this edge as an adjacent face ID. And we updated our edge face map with the new face pair, from which the ID of the popped face was also removed. And then we took the adjacent face and set it to our output parameter, which expects adjacent faces of the popped face. And if we didn't find an adjacent face, we just set it to the unset face. So that concludes the logic of our pop face method. So now let's just jump back into our header file. That's not it. Okay. So we need to implement the logic for the face visible function. Okay, this is a simple one. All we need to do is get the distance, the plane distance between the face and the point. And if this distance is greater than 0, if it's positive, then that means the face is visible. So let's just do that. So let's get the face plane distance and pass the face and the point. And if this distance is greater than 0, then that means the face is visible. But we can't check against exactly 0 because we're going to end up with some tolerance issues. So we're going to have to check it against like a plane distance tolerance. And we're going to define this in our base file or in our header file somewhere as a constant expression. As 1e negative 10. So if a point is closer to a face than this distance, then we are considering, for practical reasons, that point is on the face, and the point cannot see the face. It's just too close to actually see the face. So the face visible will return false if the distance is less than that. But there's also one more thing. The face plane distance method uses the normal of the face to calculate the distance. But it's also possible that the face's normal was not initialized or not valid. So let's just check that that is not the case. If normal is valid, then we return the face plane distance. We check using the face plane distance, and if it's not valid, then we just return false. An invalid face should always return false when checked for visibility. So that finishes that method. Let's hop back into the header file, and we now need to implement the face plane distance method. And this is another simple method. So if we get a vector that connects the test point, let me just add the names of the parameters here. So if we just get the vector connecting one of the vertices of the faces to the test point, that would look something like that. And if we take the dot product of this with the normal of the face, and we know the normal is already a unit vector because that's how we calculate the normal. So this dot product directly represents the distance from the plane of the face to the test point. And this distance is negative if the point is on the other side of the plane, not to the side to which the normal is pointing. So yeah, that's the logic of that method. So the next method that we want to define is the farthest point method. And you know what? I think I will just rename this method to get farthest point because it actually returns a boolean, so that's a bit indirect. It's not directly returning the farthest point. So I'm going to rename it to get farthest point. And I'm going to actually define the method. Okay, so let's just define it in our peek preview here. So what we need to do here is to loop through all the points that are outside, which means the points that are in our outside point set, and just find the point that is the farthest away by measuring the distance each time. So we're going to set the index, the default value, to -1 in case we don't find any points. That will be the value that will be returned, and we will set the point itself by default through an unset vector. So these will be the default values. We're going to create some variables for our loop to find the maximum distance. And I'm just going to write a normal loop that you would write to find the maximum of anything. And in the end, we have to return whether we successfully found a point or not. And we can check that by checking if the index of the point is still -1. Well, if it's still -1, then that means we haven't found a point, so we return false. If it's not -1, that means we found a point successfully, so we return true. So the next method we need to define is update exterior points. So let's just add a definition for this method, and let's go into the file and not use the peek view because this one is going to be a little bit longer than the other methods. Okay, so the first thing we need to do is to find all the points that were outside the popped faces, because we're not concerned, we don't want to waste our time going through all the outside points. We evaluate the points that have a chance of having their status changed. So we popped some faces and we closed the horizon edges off with new faces. So the points whose status is going to change are between the popped faces and the new faces. So they're outside the popped faces and inside the new faces. So let's look for points that are outside the popped faces. So for that, let's loop over all the points that are outside first and then find the candidates. So I'm going to call it OPI for outside point index. And inside this loop, so initially we have to assume that the point is outside, right? So let's just have this variable called outside, and let's set it to false. Sorry, I misspoke. Initially we have to assume that the point is inside. So that's why we set the variable outside to false. And let me just create some other helper variables here. Okay, now let's actually get the point that we're testing for. And we need to check if this point is outside any of our popped faces. So let's now loop through all the popped faces. So for each of the popped faces, we need to check if that face is visible from our test point. If it is, then that means this point is on the outside of this popped face, which means outside is true, and which means we don't need to continue checking for other faces, so we can just break from this loop. But there's also another case. This vertex, this test point, could be one of the vertices of the popped face. So let's just check that that's not the case. Because if it is, then we don't need to check for visibility. We know that it needs to be removed. So we're going to use our vector, conveniently named remove, and we're going to, every point that we decide we need to remove, we will add it to the remove vector. And we decided to remove this point, which means we don't need to do anything else for this point anymore. So we have to break out from this loop and also break out from the outer loop so that we don't waste any time here. So let's have a Boolean variable that helps us make this decision of when to break. Let's call it next PT or finished. And by default, it's false. We're not finished. And when we decide to break out of this loop, let's set finished to true. And once we break out of the inner loop, let's check if we are finished. Then let's just continue to the next point if we are finished. But if we're not finished, which means if we haven't made the decision to remove this point, then we need to do something more. We need to check if this point was outside the popped face. And if it was outside one of the popped faces, we're not sure whether we want to remove this point yet, because it could still be outside our hull, but we just need to add it to our check vector to remember to check it later. So that finishes that loop. So what we did is essentially found all the points that are outside our popped faces and added them to our check vector, and found all the points that are part of our popped faces and added them to our remove vector. So the indices that we added to the remove vector, we know they need to go. But the ones we added to the check vector, we don't know yet, so we need to check that next. So let's loop over all the indices we added to the check vector. CI for check index. Just like last time, let's assume that they're on the inside, so the outside Boolean should be set to false, and let's get the actual location of the point itself. Now we need to loop over all the new faces that are created and check if it's outside or inside. To check that, we're going to use the face visible method. and pass our test point. If it is visible, then that means the test point is outside the face, which means we have to set this outside to true, and we don't need to continue with this loop. We can just break out of the loop. So now, once we are outside this loop, if it's not outside, which means it's outside the popped faces but inside the new faces, which means it's the point that needs to be removed. So we add it to our remove vector. So now we checked all the points that needed to be checked and added the points that needed to be removed to our remove vector. The last task is to loop through all the indices we added to the remove vector and actually remove them. So that removes all the points whose inside status changed during the last operation where we popped some faces and added new faces. So that actually concludes the logic of the update exterior points method. And with that, I will conclude this video, and we will continue implementing the remaining functions in our ConvexHull algorithm in the next video. Obviously, you should be able to find the link to the source code in the description. Thanks for watching, and I will see you in the next one. Bye.